Hello dear colleagues and welcome to Civil Curious channel. In this video we are going to talk about the design of steel structures, and topics, issues that is dealing with design of structures for steel structures. Okay, this is not our just one video. I will continue these videos. I want to publish, create 5 or 6 videos about design of steel structures. Let me write our topic. Our topic is about design of steel structures. Okay. Generally, we have two types for design of steel structures, and we call them the limit state design. Our procedure is limit state design, that we call it briefly LSD. We have two popular procedure. We have two procedure for designing of steel structures in limited state design, that we call them. One of them is allowable strength design, that you all know that we call it ASD. Which is a bit old. Now we use this procedure for design of steel structures. We call it load and resistance factor design. Which briefly we call it LRFD, limit resistance factor design. Nowadays we use this procedure for design of steel structures, and we actually abandon the ASD design now. Okay, let me continue. Generally, for both method of allowable ASD and LRFD, we have this formula that tell us all of loads affected on structure, that we call it P. We call that, I want to call that P. PU should be less than a strength of structures, that we call it R. This is the whole thing that we do it in design of structures for having a safe structure. For having a safe structure, we have that formula that tells us PU should be less than R. Let me continue, everybody. In the ASD method, all of loads, don't have any coefficient to be increased, and we use uh, non-coefficient. Actually, we use non-coefficient loads, and we call them actually service loads, and another thing that we use in ASD design is the is the coefficient of safety factor. We call it factor of safety. We show that with F times S is another factor we use in ASD design. The process of work in ASD design is that all of the loads that I want to call them with F should be less than allowable force, which is equal to this is not our force, these are tension. All of existing tension should be less than allowable tension, which is equal to resisting tension of material divided by factor of safety. This is the process of work when we use ASD design, and I will solve some problem about ASD design for you. Okay, that was ASD design. Let me enter to LRFD method. Okay, in the LRFD method, which we call it load and resisting factor method, we have we have this way which called us all of existing load should be less than design load, which is equal to, which we can write that like this. We call them RU, all of existing load affected on structure should be less than phi times Rn, or resisting strength of structure. Phi is the decreasing coefficient, for designing of every element of a structure. Okay, let me go on. Okay, for the ASD method, we have 3 steps that I will illustrate that for you now. Okay, let me write our topic. Our topic is steps for ASD method. Okay, the first step is, let me change a marker. The first step is to calculate allowable tension. Calculate allowable tension, okay, which is equal to, our allowable tension is equal to, let me write that again. Our allowable tension is equal to yield tension of every element of a structure sorry. Our allowable tension is yield tension divided by a factor of safety. Now we can conclude that allowable tension, which we show that with this, F allow is equal to yield tension, which we show that with Fy divided by factor of safety. We all know that factor of safety is a number greater than 1. You all know that factor of safety is a number greater than 1. Okay, and factor of safety is different for example calculating in is different, for example, from flexural moment to, for example, torsional moment. When you want to calculate a axial force, you don't have that factor of safety when you want to calculate the for example, flexural moment in every element. Okay, the second step is to calculate internal tension in element. Okay, let me write that again. The second step is to calculate internal tension in elements. Okay, this is the second step, and the third step is to compare all of the tension all of the tension which is about the loading to our tension in element, okay, resisting tension in element. We have tension resulted by loading should be less than resisting or allowable tension. Should be less than allowable tension, which we can write that this tension which is resulted by loading should be less than allowable tension. Okay, these were the steps for allowable for ASD design or allowable strength design. We will solve some problem for that and continue. Now let me share the method, or let me share the method of LRFD and tell you the steps for LRFD design. Okay, let me write our topic. Our topic is steps of LRFD design. Okay, the first is I told you in the first minutes of our course that LRFD is the new way. You know, we can now we don't use of ASD design in design of steel structures. Okay. The first step is to calculate nominal strength of section. Calculate nominal strength of section. Okay. And the second step is to calculate the design strengths of section. Okay, which we call we show that with Rn. Okay, let me write that. The second step is to calculate design strengths of section. Okay, we show the nominal strengths with Rn, and we show the design strengths of section with phi, which is decreasing coefficient times Rn. Okay, we call the, let me write that, we call the design strengths Rd, which is equal to phi times Rn. Okay, phi is always a coefficient that less than 1, which is different from fractional to torsion to shear. You know, you can memorize that, the coefficient of phi, and you don't, if you don't want to memorize that, you can calculate that from the basic code like AISC 360 and 16. Okay, actually it's important, I want to write that phi is always a coefficient less than 1. You have to memorize that. And the second step in LRFD design is to compare the design strengths and nominal strengths. Okay, in the second step, in the third step, we calculate the all of loads affected on a structure. You have to know that these affected loads have a coefficient greater than 1. You know, because in design of a structure we consider the affected load greater than 1, and we increase them by some coefficient that we call them load of combination of loads, you know, and we decrease our strengths of elements. You know, this is the whole procedure of LRFD design. You know, in this in the third steps, we actually calculate affected loads on a structure, RU. Actually calculate RU. You know, that must be calculated that must be calculated with increasing load. Okay, this is the procedure. And in the fourth step, we will compare the all of loads resulted by all of the loads resulted by loading, you know, to nominal strengths of a structure. Let me write that for you. All of the actions resulted by loading should be less than design strengths. You see, which we can write that in math format. Actually, we have RU, which is acting of a structure in a structure, should be less than RD, the design strength, which is equal to phi times Rn. These were the general steps for two procedure of design in steel structures, ASD and LRFD, which we explain for you the steps for them. Okay, let me go on. I hope that you all don't be tired, and if you feel so like me, you can drink a tea and continue. Okay. For your break time, I want to tell you that what does the coefficient that increase our loading mean. Actually, suppose that we have a simple beam and there is a loading on it. Okay, the length of beam is L, and the loading included both dead and live load. We have both dead and live loads. Okay, and I want to tell you what the increasing coefficient, what does the increasing coefficient mean? In the LRFD design, we have a coefficient for dead loads for dead load, that we call them gamma of dead load, and we have a coefficient for live load, which we call that gamma of live load. Okay, and the ultimate loading, or QU, and the ultimate loading is equal to QU is equal to gamma of dead load times the QD plus the gamma of live load times the value of live load. You know, this is the procedure. Okay, and when this is the procedure of calculation, okay, and when we want to calculate, for example, a maximum fractional moment effected on this beam, we have, for example, the maximum fractional moment is QU times, you know this formula, square meter of L divided by 8. Okay, which this QU is this QU, which is equal to gamma DL times QD plus gamma LL times QL. Okay, this is actually the comprehension of of increasing coefficient in the LRFD design. Okay, let me go on. And let me, if you all, maybe you all know that, what is the main difference between ASD and LRFD design? You know, and I'm gonna illustrate that for you. What is the main difference between ASD and LRFD design? Let me write our topic. Let me ask my question. What is the main difference between ASD and LRFD design? Okay, the main difference is in the ASD method, we have comparison between tensions, you know, and in the LRFD design, we have comparison between loads and moments, you know. This is the main difference. And the second one is in the ASD design, we don't increase our loading, you know, and all of them has the unit coefficient. But in the LRFD design, we increase our ultimate loading. Okay, and maybe you're wondering that how can we find the value of this increase? In the ASCE, you know, in the ASCE code, which is loading code that all of engineers should obey, that we have this increase, the value of this increase in load combinations, you know. ASE have some load combination for us in design of both concrete structures and steel structures, and we can use of these coefficient, you know, and we increase our ultimate loading with these coefficient. Okay, so if you all agree, I want to write these differences, the main differences for you. As I said, now the first difference is in the ASD design, we compare we compare tensions, but in the LRFD design, we compare loads and moments. In the ASD design, we don't increase ultimate loading. We don't increase the value of ultimate loading, and but in LRFD design, we actually increase the value of ultimate loading. These were the main differences. Now, if you all agree, I want to solve a coefficient for you. I want to solve a problem for you, and I want to solve that with both ASD and LRFD method, and we compare the result with each other. Okay, if you all agree, let's get started. In this problem, we have a tensile plate with a fixed connection, sorry, I want to draw that for you. Okay, we have the force of dead load 10 ton force, and we have the live load 14 ton force. Okay, and we know that our yield strengths of material, all of the steel material have yield stress of 2,400 kilogram divided by square meter of centimeter. Okay, and what the problem wants us is that is to calculate the thickness for this plate in both ASD and LRFD method. Okay, in both ASD and LRFD. Okay, let me solve this. we have the width for the section of this plate as 10 centimeter is the width of plate. Okay, in ASD method, first of all, we enter to ASD method. In ASD method, first of all, we have to calculate the allowable tension. Okay. First of all, I want to calculate the allowable tension, which is equal to the allowable tension, which I want to show that with Ft is equal to yield stress of plate divided by the divided by safety of factor, which in the tensile case we have the safety of factor 5 divided by 3, which is equal to 0.6 times Fy, which is equal to 1440 kilogram divided by square meter of centimeter. Okay, in the ASD design, we actually decrease our yield stress, and this factor of safety is different from, for example, tensile case to shear case to fracture moment case, and etc. Okay, and in the second step in ASD design, we calculate the tension resulted by our loading, which is equal to the second step. We calculate the tension resulted by loading. Okay, that our Ft is equal to P divided by A. When you want to calculate the tension in tensile case, the result is this load P divided by the area or section, which is equal to, we have the value of P. Let me clean that. We have the value of P. We have the value of P 10 plus 14, and this is the value of P, and the value of section is 10 centimeters times T. We don't know the thickness of this plate, but we know that the width of this plate, and the area of section is 10 times T. These all of T and 10 are in centimeter unit, but we have the load in ton, so we have to multiply the value in above of this, divide times 10 to the power of 3 cubic meter of 10. Okay, and the result is 2400 divided by This is the result. Now we compare the tension resulted by the loading to allowable tension of elements. Okay, in the third step we have Ft should be less than Ft, that we have 2400 divided by T should be less than 1440, and from this equation we can calculate the value of T, which is equal to 1.67 centimeter. This is our result in ASD design, and this is not the end. Now I want to calculate this problem with LRFD method for you, and then we compare. But remember that the value of thickness in ASD design were 1.65 centimeters. Okay, let's start LRFD design. Let me write that. Let me write that with LRFD design. Okay, in the LRFD design, in the first step we have to calculate the nominal strengths of elements. Okay, in the first step we have to calculate the nominal strengths. Okay, the nominal strengths Pn is equal to yield stress times Ag, which is equal to our yield stress is 2400 times the gross section area is 10 times T. This is the ultimate strength that our section could endure, which is equal to 24,000 times T. Okay, and in the second step we must calculate the design strength. Which is shown by PD, which is equal to Pht times nominal strength. Pht is the tensile decreasing coefficient, as I said you before in the past slides. Okay, and from the AIC code we have the Pht, or the coefficient or decreasing coefficient of tension, as 0.9. Okay, remind that PD is equal to Pht times Pn, which is equal to 0.9 times 24000 times T, which is equal to 2160 times T. Okay, this is the design strengths, and now we have to calculate the loads resulted by loading. You know that we have to increase our loading in our LRFD design. Okay, let me write that for you. The third step is to calculate the action resulted by loading. Okay, that our PU is equal to from the ASCE 7 we have this method for increasing the load. Remember that what I'm writing now is from ASCE code. Our PU is 1.2 times PDL according to ASCE plus 1.6 times PLL according to ASCE. 1.6 is the coefficient that is used for actually increasing the for live load, and 1.2 is the increasing factor for increasing the dead loads. Okay, now we have 1.2 times 10 plus 1.6 times 14 live load. Okay, and all of them times cubic meter of 10, because we want to calculate in centimeter unit. Okay, and the result that I've calculated already is 34 and 40 kilogram force. Okay, now in the fourth step, as I explained the steps for you, in the fourth step we compare the resulted load by resulted loading should be less than design load. Okay, or design strength, that our design strength is equal to Vt times Pn, that we have already calculated that, and the answer is 34,400 must be less than 21,600 times T. Okay, everybody, and the resulting T should be greater than 1.59 centimeter. Okay, this is the method for calculating thickness of this plate in the LRFD design. Okay, we have I have introduced two ways in design of steel structures where ASD and LRFD for you. Okay, and I told you LRFD design is nowadays more general, and most of designers use this procedure, and I want you all to use this procedure in your design. Okay, and I know that you use that. Okay, and in continue, I have illustrated the steps in design of LRFD and ASD for you. Okay, and in the end, I've calculated one problem for you to get more familiar with these two methods. Okay, as you can see, the answer for sickness from LRFD design is 1.59, and in the ASD design is 1.67, which is greater than in LRFD design. I have to tell you, this result is not always occurs, and according to our loading would be different. Okay, I want you now finish our session in ASD and LRFD design. Okay, and in the next sessions I will enter to introducing, for example, steel material and the properties of a steel material, and introducing steel profiles actually, which are really important, and the parameters in steel sections like moment of inertia, section, and for example, plastic section modulus, elastic section modulus. These are very, very important, everybody. Radius of gyration, and such a things. Okay, and in these minutes that I have that, I want to tell you some new things in steel structures. Let me tell you that we have now I want to tell you this. I want to tell you some important thing that I want you all to know. That I want to ask a question actually of you, that what is limit state in structures. Okay, what is limit state? Let me write like so. Limit state is referred to condition that if all or parts, if all or some parts of structures achieve to this state, then will no longer be able to do their duties. You know, this is the definition of limited state that I've thought maybe it be useful for you. Maybe one day you are in engineers gathering, or maybe somewhere you hear that, and maybe someone asks you, what does limited state mean? That was all, everybody, for our session. I hope that you all enjoy it. In the next videos, we continue our sessions about steel structures, because I love steel structures actually. If you like it, please subscribe to the channel to motivate me to create more videos for you, and I want you all to support. Please support the channel. Thank you very much.